Hello friends, today we are going to see how we can understand clampers and peak detector circuits in fewer minutes. So let's start with the very basic concept that we know. We know that clamper is divided into two types, that is it can be positive clamper, it can be negative clamper. For positive clamper we know that the output waveform will shift upwards, and for negative clamper we know that output waveform will shift downward. Basically this clamper shifts the DC level. You can see this is our input waveform. If it is passed from positive clamper, you can see the DC level is shifted from 0 to Vm. Okay, similarly for negative clamper, here this is your input waveform. The DC level of this waveform is 0, and if it is passed from negative clamper, you can see it is shifted to minus Vm, but the peak to peak voltage remains same. So you can see the input waveform has peak to peak voltage of 2 Vm. Here also you can see the peak to peak voltage is 2 Vm. Okay, 0 to 2 Vm. You can subtract maximum voltage to minimum voltage to get your peak to peak voltage, right? So you can see here Vm minus of minus Vm is 2 Vm, 2 Vm minus 0, it is 2 Vm. Okay, similarly you can see for negative clamper also, this waveform is also having the same peak to peak. You can see 0 minus of minus 2 Vm, it is nothing but 2 Vm. Okay, so you can see the peak to peak voltage remains same, the waveform remains same, but the change is only in the DC level. Okay, if you want output, you can see the output of positive clamper is VO equals to Vi plus Vm. Okay, and Vm is the peak value of your input voltage. Okay, because of this only you will get your output DC level shifted. Okay, this is the DC level. Initially it was 0, now it is shifted to plus Vm. Okay, and similarly for negative clamper, you can see the output will be VO is equals to Vi minus Vm. Okay, initially it was VO is equals to Vi minus 0, now it is changed to VO is equals to Vi minus Vm. DC level is shifted to minus Vm. Okay, we will see this thing in detail. This is just a quick review of what we know actually. Now let's see peak detector. We know peak detector is divided into two types: positive peak detector, negative peak detector. Positive peak detector will detect the positive peak, while the negative peak detector will detect the negative peak. Okay, so the output of positive peak detector will be the maximum input voltage, positive maximum input voltage, while for negative peak detector it will be negative maximum voltage of input waveform. Okay, or you can say it has minimum input voltage. Okay, now let's see this thing into detail. Okay, now let's start with the positive clamper circuit. This is the circuit of positive clamper, and the input waveform given to this circuit is this one. Okay, so let's start the working of this circuit. Initially we assume that capacitor is uncharged. Okay, now let's start with the positive half cycle. So you can see for positive half cycle, this diode will be off, right? Since we know that capacitor is uncharged, so it is nothing but Vc is equals to 0. If voltage is equals to 0, it means that it will replaced by short circuit. Okay, if it is replaced by short circuit, it means that this voltage is directly given to this diode, and you can clearly see that for positive input waveform, this diode will be in reverse biased. Okay, so we can say for that time this diode will be replaced by open circuited. Okay, now if capacitor wants to charge, it has only one path to charge. Okay, that is from RL, and RL here we know it is very high. Note one thing, the mandatory condition for clamper circuit is that RL should be very high. Okay, either it can be infinity, that is it should not be present there, or if it is present there, then the value of RL should be as much high. Okay, to get the clamper action. Okay, so always you will get RL very high, or it won't be there in the circuit. Okay, so you can see for the capacitor to charge, it has only path from RL. Okay, so if we find out the charging time constant, you can see tau c will be RTH into C. RTH here, if we have only RL, RL is very high, so we will say that RL into C will be very much high than the time period of this input waveform. Okay, so we can say the capacitor won't charge in this phase. Okay, so now let's see for negative half cycle. So here you can see for negative half cycle, this diode will be on. Okay, clearly it can be seen like for negative input waveform, you can see this diode will be in forward bias, negative to negative, positive to positive will be connected. Okay, so at that phase where you know the diode is getting to turned on, always you have to consider the half waveform. Okay, so for negative waveform I am considering first for t by 2 to 3 t by 4. Okay, so you can see I have considered this t by 2 to 3 t by 4. I will say the diode will now be on. Okay, so either it will be replaced by short circuit or it will be replaced by RF and voltage source of 0.7. Okay, it is a piecewise equivalent model. I hope you know it. We know that output voltage is nothing but voltage across this RL, which is nothing but voltage across this diode. Okay, so if this diode is on, it is replaced by short circuit, so at that time output voltage will be 0. If it is replaced by any other voltage source, then the voltage corresponding to that voltage source will be the output of this circuit. So we can say at this phase output voltage will be nearly approximately equals to 0. As we know, for the diode in on condition also it has a voltage 0.7 volt, right? So we will say it is nearly equals to 0. So we get to know diode is on, VO is nearly equals to 0. So now if the capacitor want to charge, it can charge from the resistance provided by these two branches. Okay, so you can see now the diode is on. Okay, so the resistance provided by this diode will be very less. Okay, either it will be 0 or it will be somewhere around 10 ohm. Okay, so let's consider this as 10 ohm and this as 10,000 ohm. Okay, so you can see we have RTH right now as 10 parallel with 10,000, right? Always if you have to calculate the RTS, what you have to do is you have to see by opening your capacitor. Okay, so if you see from your capacitor side, you will find that this diode resistance and this RL is in parallel. Okay, so you will say diode resistance is in parallel with this RL. Okay, so we have considered this much value such that we can estimate what will be the equivalent resistance for capacitor to charge. Okay, so you can see this will be 10 into 10,000 upon 10 plus 10,000. Okay, and if you calculate in calci you will get somewhere around 9.99. You can see it is nearly equal to the resistance provided by the diode itself. Okay, always note one thing: if your two resistance is in parallel and if one resistance is very small and one resistance is very high, then the equivalent resistance will be approximately equal to your smaller resistance. Okay, so this is what we are getting here. So we can say now we have resistance equivalent as RF. Okay, so we can say for capacitor to charge, the time constant will be RTH into C, which is nothing but RF into C, which is very much small as compared to RT of this waveform. Okay, so we will say the capacitor at this time will charge very fastly to the value Vm. Okay, so now the question is how I get to this Vm. Okay, so for that you have to follow one thing. Here the capacitor voltage polarity will always be decided by the polarity of this diode. Okay, so you can see N is here, P is here. First we have negative terminal, that is cathode terminal, and then we have positive terminal, that is anode. Okay, so for capacitor also first we will write minus here, then we will write plus here. Okay, so what we are doing is we are fixing the polarity and we will change the magnitude. Okay, so we will always follow this polarity and our magnitude either can be Vm and minus Vm. Okay, we are doing this thing such that we won't be confused in further process. Okay, so now we get to know the polarity of this capacitor will always remain this thing. So now we know the polarity of capacitor. We just want to know the magnitude of this capacitance voltage. So for that you can follow this circuit. So here we know that diode is in on condition. So that's what I have replaced with short circuit. Okay, so now if you use the KVL, so you can see we will have plus VC plus VI is equals to 0. So we will say VI plus Vc is equals to 0. Okay, now if you take Vi at this side, you will get Vc is equals to minus Vi. Okay, and at this phase we know Vi maximum voltage is minus Vm. Okay, so you will write in place of Vi as minus Vm. Okay, so you will get the magnitude of the capacitor voltage as plus Vm. Okay, so that's what I have written here. Okay, so always you have to follow this thing, that the polarity of the capacitor will be decided by the diode terminals and the magnitude will be decided by the KVL. Okay, yeah, I know you may be thinking why I am using the polarity of diode to judge the polarity of capacitor. So for that you can always follow the property of diode. As we know, diode is a unidirectional device, right? So it will always allow the current to flow from anode to cathode. Okay, so you can see we know that the current can flow from P to N. It means if the capacitor have to charge, it has to follow this path only. So always this terminal of the capacitor will be positive and this terminal will be negative, right? Because the capacitor is charging this way, right? So this terminal will be positive and this terminal will be negative, right? So that's why I am saying, instead of thinking analytically, just use the terminal of the diode to get the polarity of the capacitor voltage. Okay, so stress will be less and you will get the same result. Okay, so now let's move ahead. So till now we have seen for this waveform and for this waveform. Okay, so now we are going to see for this waveform. Okay, and one thing that we get from this waveform as that the capacitor voltage have this polarity and the magnitude is Vc is equals to Vm. Okay, now let's see for t greater than 3t by 4. So you can see Vc t is equals to 3t by 4 plus it will be equals to Vc 3t by 4 minus, right? You can see the capacitor voltage at this point will be equals to at this point. Why? Because you know the capacitor voltage opposes the change in voltage. Okay, so the whatever the capacitor voltage present here will be same as here. Okay, but input waveform is continuously changing. Okay, so at this point it will be somewhere around minus 10, so at this point it will change to minus 9.9. Okay, so I'm just giving an example. Okay, so let's use the same example to move further. So now we have considered that Vm is equals to 10 volts. So it means that we have considered that this sinusoidal waveform has 10 sine omega t. Okay, so the maximum will be plus 10 and the minimum will be minus 10 volt. Okay, so that's what I have written here. Vm is equals to 10 volts. So at 3t by 4 plus Vi will be minus 9.9 volt. At this point it will be just less than minus 10 volt. Okay, so I have considered minus 9.9 volt, but capacitance voltage will remain same. Okay, so now we have to check whether the diode will remain on or off. Okay, so for that we have to find out this Vd I have considered minus upside and plus downside corresponding to the terminal of this diode only. So you can see if we apply KVL, so you can see if we apply KVL to this mesh, you will get plus Vi plus Vd plus Vm. Okay, plus Vi plus Vd plus Vm, which is nothing but 10 volt is equals to 0. So now Vd will be is equals to minus 10 minus Vi. Okay, Vi we know it is minus 9.9. Okay, so if we replace minus 9.9 here, we will get minus 10 plus 9.9, which is nothing but minus 0.1. So you can see Vd is less than 0 volts, so we will say diode will be off. Also you can see if the diode wants to on, the input voltage should be less than minus 10 volts. So either it can be minus 11 or minus 12, right? So if we replace minus 11 here, you will get minus 10 plus 11, which is nothing but 1 volt, which will be greater than 0 volts. So at that time only we will say that diode will be on. But you can see the maximum voltage that our input waveform have is 10 volt. Okay, which cannot go beyond minus 10 volt, right? So at this phase we will say the diode is not going to turn on again. Okay, so now we get to know that this diode is disconnected from the circuit and now we have only this circuit. Okay, so now from this circuit, if the capacitor wants to discharge, it have to discharge from this RL only. Okay, so if we calculate our discharging time constant, you will say tau d, it is nothing but RTH into C. RTS for this time it is nothing but RL, so we will say RL into C. So you can see this value is much higher than the time period of our input waveform. So we will say at this time the discharging of capacitor won't happen. Okay, so at this phase the capacitor will be simply acting as a voltage source with the voltage of Vm. Okay, so at the end you will get only this input voltage, this voltage source and this resistor at your out. Okay, now if you try to apply KVL, what you will get? Minus Vo plus Vm plus Vi. Okay, minus Vo plus Vm plus Vi is equals to 0. So Vo will be Vi plus Vm, and you can see this is the equation of clamper. I hope you got the whole explanation and you understand how this equation comes. So the waveform you can see for the positive phase, this diode was on. So whatever the input voltage is present here, it will be simply present at the output. Okay, so you will get the same waveform here. And for the negative waveform, for this phase you can say the diode was on, so the output voltage will be simply 0. So that's what I have written here. And for this phase you can see the diode was off and the capacitor was replaced by a voltage source. Okay, so from this phase we were able to see the clamping action. Okay, so if you try to find out the voltage at this time, you will get the double of your input voltage. Okay, so here if it is Vm, you will get here 2 Vm. Okay, so this is nothing but a clamper waveform, and you will always find that the clamper waveform starts always after one time period. Okay, so this is the basic thing that you should know it. Okay, now let's see the negative clamper. In positive clamper, the diode was upward, but in the negative clamper, it is downward. Okay, so let's start with the positive half cycle. So you can see for the positive half cycle, only this diode will be on. Okay, so whenever we come to know that diode is going to turn on, we have to start checking from half of the waveform. Okay, so now we are going to start with this phase. Okay, 0 to t by 4. So for 0 to t by 4, we will say diode is on. So either we will replace by short circuit or we will replace by RF. So you can see the resistance equivalent will be very much small. Okay, so the path for the capacitor to charge will be from the equivalent resistance provided by these two branches. As we know, the resistance equivalent of these two branches is very small, so we can say tau c will be nearly equals to 0, or it will be very less as compared to the time period of this input waveform. So we will say the capacitor will charge instantly to the maximum input waveform. Okay, and as we discussed, we have to always use the polarity of diode to get the polarity of capacitance voltage. So here you can see we have plus here, then minus here. So we will use the same polarity, plus here, then minus here for VC. So now we are remaining with the magnitude of capacitance. So for that, what I have done, I have replaced this diode with the short circuit. As we know, for this phase the diode is on. If you apply the KVL, you will get minus VI plus VC is equals to 0. So VC will be equals to VI, and at this time the maximum voltage of input waveform is plus Vm. So at this phase you will get the capacitor will charge to plus Vm. So now let's see for the phase t greater than t by 4. Okay, so you will now say that Vc t by 4 plus will be is equals to Vc t by 4 minus. As we know, the capacitance opposes the change in voltage, it will be equals to 10. We have considered that this waveform as 10 sine omega t. So the Vm here we have a 10 volt. Okay, so we will say the capacitor will be charged to plus 10 volt. Okay, this is what I have written here. Vi t by 4 plus will be less than 10 volt. It will be nearly 9.9 volt. Okay, so now again we will check whether our diode is in on condition or off condition. Okay, so for that we will apply KVL. So you can see minus Vi plus Vc plus Vd is equals to 0. So for Vd it will be Vi minus Vc. Vi we know it is 9.9 less than 10 volt. Okay, minus 10 volt it is minus 0.1 volt. So you can see Vd is less than 0 volt. So we will say the diode will be off. For diode to be on, the input voltage should be greater than 10 volt, which cannot be possible, as we have seen the input voltage has a maximum voltage of 10 volt. Okay, so we will say diode will no longer can be turned on. Okay, so at this time this diode will be replaced by open circuit, and the only path for the capacitor to discharge will be this RL. Okay, so if you calculate the discharging time constant, you will get RL into C. RL is very high, so the capacitor won't be able to discharge. So we will say capacitor will be simply replaced by voltage source. So if you calculate the output voltage now, you will get minus Vi plus Vc plus Vo is equals to 0. So Vo will be is equals to Vi minus Vc. Okay, this is what I have written here. Vc we know it is nothing but Vm. Okay, so this is what I have replaced here. Vo will be is equals to Vi minus Vm. This is the final output of the negative clamper. Okay, this is what we have seen in the basic discussion also. Now let's start with the peak detector. First one we have positive peak detector. The difference between the peak detector and the clamper is that the diode position and capacitor position. You can see for clamper diode was present here, but in peak detector it is present here. Okay, just we have changed the position of capacitance and diode to get the peak detector. Okay, so let's start the working here. So for positive half cycle, you can clearly see the diode will be on. Okay, so whenever the diode is on, we have to consider the half of the waveform. Okay, so you can see the half of this phase is this portion. Okay, so we'll say for 0 to t by 4, this is what I have written here, 0 to t by 4, diode will be on. Capacitor will charge to plus Vm. Why? Because you can see the capacitor will get the charging path through this diode. Okay, and you can see the resistance provided by this diode will be very small. Okay, so tau c of this capacitor will be nothing but Rf into C. Rf into C is very small as compared to the time period of this waveform. So we will say the capacitor will charge instantly to the maximum input waveform. Okay, So this is what we get the magnitude of the capacitor. But what about the polarity? Polarity always will be the same as of diode. Okay, so here it is plus minus, so here also it will be plus minus. So now we get to know the polarity, and we know that the magnitude of capacitor is plus Pm. You can verify it by short circuiting this diode, as we know the diode is on at this phase. Okay, so we can replace by short circuit. Okay, so if we replace by short circuit, we will get minus Vi plus Vc is equals to 0. Okay, minus Vi plus Vc is equals to 0. So we will say Vc is equals to Vi, which is nothing but is equals to Vm. Okay, so now at this phase we get to know the polarity of capacitor voltage, we get to know the magnitude of the capacitor voltage. Okay, so now we will check for the phase for t greater than t by 4. At t by 4 we will say that Vc t by 4 plus will be is equals to Vc t by 4 minus. Okay, this is what we are following the same procedure of the clamper. Okay, then we will say Vi t by 4 plus won't be equals to Vi t by 4 minus, right? As you can see, the capacitor opposes the change of voltage, but the input waveform is continuously changing. Okay, so we will use this thing into consideration. So now we have to check whether the diode will be on or off. Okay, so for that we have to find out the voltage across this diode. Okay, that is nothing but Vd. So if you apply the KVL, you will get minus Vi plus Vd plus Vc is equals to 0. Vc is nothing but Vm. Okay, so Vd will be is equals to Vi minus Vm. Okay, Vi we know at this phase it can be 9.9 if we consider the input waveform as 10 sine omega t. Okay, it won't be 10 volt, it will be somewhat less than 10 volt. Okay, so we have considered 9.9 here. 9.9 minus 10 is nothing but minus 0.1. Okay, which is less than 0. So we will say diode is off. For diode to be on, input waveform should be greater than 10 volt, which cannot possible. So we will say diode cannot be turned on again. So we can replace this diode with open circuit. Okay, so we will be remaining with this circuit only. Now if the capacitor want to discharge, it can discharge from this RL, but we know RL is very high, so the discharging time constant will be very high as compared to the time constant of this input waveform. So we will say the capacitor won't be able to discharge, it will be replaced by a voltage source with the voltage of Vm. Okay, and the polarity will be followed by the polarity of capacitor voltage. Okay, so we will get this circuit Vm with this polarity and Vo as this. So we will say Vo will be simply Vm. Okay, so this is the output voltage of positive peak detector, which we have seen in the basic discussion. Okay, now let's move ahead to the negative peak detector. So this is the circuit of negative peak detector. You can clearly see the difference. The difference is only in the placement of the diode. Earlier anode was here, cathode was here, but here we have anode here, cathode here. Okay, so now let's see the working. So for positive half cycle, you can see the diode will be off. So you can skip this waveform. For negative half cycle, you can see the diode is going to turn on. Okay, so we will consider for half of the portion, which is nothing but T by 2 to 3 T by 4. So at this time we will say the diode will be on and the capacitor will get the charging path through this diode. As we know, the diode resistance can be RF or it will be simply 0 ohm. Okay, so the charging time constant for the capacitor will be very small, so we can say the capacitor will be charged. The polarity will be very similar to the diode polarity. Okay, so you can see we have first minus then plus. Okay, so the polarity of capacitor will be also same, that is minus first then plus. Okay, so we know the polarity right now, we want only the magnitude. Okay, so for magnitude we will replace this diode with short circuit, and you can see plus Vi plus Vc is equals to 0. So Vc will be equals to minus Vi. We know the input waveform can go maximum up to minus Vm. Okay, so we will say minus of minus Vm, so we will say the capacitor will charge to plus Vm. Okay, so we are completed with this phase. Now we are remaining with this phase. So now for this condition we have to check whether the diode will remain on or off. So for that we have to find out the diode voltage. Okay, so we will apply the KVL and try to find out that. Okay, so we have plus Vc plus Vd plus Vi is equals to 0. Okay, Vd will be is equals to minus Vi minus Vc. Vi at this time will be less than the capacitor voltage and it will be negative. Okay, so we will say Vi can be minus 9.9 and Vc will be minus 10. As you know, the capacitor opposes the change in voltage, but the input waveform will keep on changing. Okay, so we'll have minus of minus 9.9, which is nothing but 9.9 minus 10 is equals to minus 0.1. Okay, So VD we get negative. Okay, so we'll say the diode will be off, and if the diode want to on, so for that the input voltage should be less than minus 10 volt, which is not possible as we have input waveform of 10 sine omega t. Okay, so the maximum voltage can be plus 10 volt, and the minimum voltage will be minus 10 volt. Okay, so we will say after this phase diode will no longer be on. Okay, so we can replace the diode with open circuit and we will be remaining with this circuit only. So now if the capacitor want to discharge, it can discharge from this RL, but we know this RL is very much high, so we will say the discharging time constant, which is nothing but RL into C, will be very much greater than the time period of this input waveform. So we will say capacitor no longer will discharge and it will be replaced by simple voltage source with the magnitude of Vm. Okay, so we'll get plus Vm plus Vo is equals to 0, which is nothing but Vo is equals to minus Vm. This is the output voltage which we have seen in the basic discussion also. Okay, so I hope you understand everything from positive clamper to negative peak detector. You have to follow this step only and you will get output waveform and output equation correctly without any mistake. Okay, so that's it for today. Thank you guys.